recall that the product, cross product of two vectors is the output is a vector, okay? Its magnitude is norm A, norm B, and sine theta. Theta is the angle between these two vectors. And this direction of this vector is determined by the right-hand rule, okay? By the right-hand rule. Now, this is only defined in R3. In higher dimensional space, we can't do that, okay? Because in R4, in a fourth dimensional space, now if you have a line, now you can find three other lines that are perpendicular to each other. So you don't have a unique defined perpendicular direction, okay? So cross product is only determined in dimension 3. So now the base vector I cross j we get k, j cross k we get I, k cross I we get j. So we have a cycle I j k, okay, a cycle, and the cross product satisfies the Euler nice property distributive law. And by definition, A cross B, the norm of this vector gives us the area of the parallelogram, where the two sides of the parallelogram is determined by the two vectors A and B. And we find that A cross B, in this case, A cross B, in this case, in coordinate form. Now in dimension 3, IJK, we plug in a coordinate, then we finally get this, okay? It's hard to remember directly the result. Then we use this notation, use this notation to remember we use this determinant, 3x3 determinant to remember this. Then we give one example. We give example how to compute this, okay? How to compute this. Okay, now we give more examples. Now I'll give you all more examples for cross product. So let's see this example. Okay, now we want given 3 points in R3. Okay, so we want to find, so the 3 points determine a plane. So find a vector that is perpendicular to a plane. Find a vector perpendicular to the plane that pass through 3 points. That passes through P, 3 points. Okay, 3 distinct points. You know, if they are not lie in one line, they determine uniquely a plane. Okay. So it's easy to check that these 3 points is not on a plane. It's not on one line. So they determine a plane. Now we want so suppose you have 3 points P. Let me plot. So you have 3 points PQ, maybe PQR. Now we want to find a vector that is perpendicular to these 3 vectors. Okay, PQR, PQR. So we just plot a picture. Okay, we want a vector N that is perpendicular to the plane determined by PQR. Well, we can do the following. We can find PQ and we can find PR. PQ is a vector head minus tail. So we use the coordinate of Q subject the coordinate of P. Then we get coordinate. So this is so Q subtract P. So negative, so X component -2 minus 1, so we get a -3. Y component 5 minus 4, so we get a 1. Okay. Z component -1 minus 6, so we get a -7. Okay. So what is PR? What is PR? PR, we again use head minus tail. Okay, y minus 1, so we get a 0. Negative y minus 4, so we get a negative 5. And then y minus 5, y minus 6, so we get a negative 5. Okay, coordinate of r minus coordinate of p. Okay, now we know, remember this, PQ, cross product. Then we use cross product. PQ, cross product PR, is perpendicular to PQ and it's perpendicular to PR. So this is a vector. Is a vector. Perpendicular. You know, by definition, cross product of two vectors is a vector that is perpendicular to both of these two vectors. Okay, by the right hand rule, is perpendicular to PQ and PR. So of course, this cross product, the output of the cross product should be perpendicular to the plane. Okay, perpendicular to the plane. So we can choose the vector to be our design vector to be PR cross PQ or PQ cross PR. So then we find what explicitly PQ cross PR is by the coordinate form. So first write down IJK, and then write PQ and PR. PQ is -3, 1, -7. Okay, PR is 0, -5, -5. Okay, and then we remember this is a convenient way to help us to remember the output. So the I component, what we get for the I component is, so let me cross the I component in red, plot the I component in red. So when we do this, what we do is to find the I component, then we cross out the row and the column that contains I. Okay, cross out the row and the column of I. So what is remaining is, let me cross out, use red. So the red cross out. So the row and the column that contains I. Then the remaining thing will be, so let's use the red. The remaining thing will be 1, -7, -5, -5. Okay, so this is remaining 2 by 2 determinant. Remember, we already defined it in this manner. We already defined 2 by 2 determinant. And then for the G, now for G, now we alternate everything. Every time we alternate it by -1. So the first, when we do I, we get a positive I, and then J, we do minus J. So the sign, the alternating factor -1 is to the power, so the -1 to the power column number, so column number plus row number. So for G, it's in row 1, column 2, so it's actually 3, -1 to the power 3, so we get -1. So it's a column number plus row number. Okay, for G, its column number is 2, row number is 1, so it's -1 to the power 3, so we get a -1. So G, I think what we get is, let's use, we cross out the row that has G, row and a column. So it's cross out this one and then cross out this. So the remaining thing is, you see, we have -3, 0, -7, -5. So this, what is remaining when we expand at J. And then for K, now K is in the first row, third column. Then, so we get row number is 1, column number is 3. So it's 1 plus 3, we get a 4. So -1 to the power 4. So we get a plus, okay, plus K to the power, to the coefficients. Now we cross out the column and a row that contains K. So what is remaining is -3, 0, 1, -5. Okay. So then the 2 by 2 determinant, we already know how to we already have a definition. So this we get I 2 by 2 determinant. Okay, 2 by 2 determinant. So this is a 1 times -5 minus -7 times -5 minus g. This is -3 times -5 minus -7 times 0. Now plus k, the last k, -3 times -5 minus 1 times 0. Okay, so finally we compute this. So we get a -40. So this we get a -40i. Just evaluate that thing. For the coefficient of g, -3 times -5, so we get a 15. And then the other term is 0. So it's minus 15g. And then for k, 3 times 1, we get -3 minus 5, -8. Oh, sorry. So I'm confusing myself. So it's -3 times -15. -3 times -5, so we get a 15. So plus 15k. Okay. So the vector that a possible vector that perpendicular to the plane is this vector. So it's a -40i minus 5g 15g plus 15k. So it's a coordinate form. It's a -40 -15 15. Okay. If you factor out the common factor 5, so you can also find another possible choice. For instance, let's do divided by 5. So divided by common factor 5. So we get this vector. Okay. Now the vector is not unique. We can scale by any non-zero scalar. Okay. So we only need the direction. So you check this vector 8 -3 3 is perpendicular to a PQ. Remember what is PQ? You can also check PQ is -3 1 -7. If you do so this is n, let n be this. If you let n dot product with PQ, you check so you get 8 -8 times -3 then plus -3 times 1 plus 3 times -7. Then you get this you get 24. This -3 minus 21. This is exactly 0. So we get a perpendicular relation. You can also check with PR. PR is 0 -5 -5. You just check n cross n dot product with PR. Then you get a -8 times 0 plus -3 times -3 times -5 plus 3 times -5. So you get this is 0. This you get 15. This is minus 15. So you get a 0. So this is also perpendicular. Okay. So this is indeed the normal vector. Okay. This is a normal vector perpendicular to the plane. Okay. A normal vector to the plane PQR. So from those 3 points, we can determine the normal vector. We can also write down the equation of this plane. Write down the equation of the plane. Remember, so we have a point. So to write down the equation of the plane. So this is normal vector n. Now any point. So suppose this is the point P on on the plane. So any point. Let's do P prime. P prime be any point. So then P, the vector. Then the vector P P prime. This vector P prime will be orthogonal to the normal vector. Normal vector. So this is equivalent. So P prime is in the plane. Is equivalent to P prime. This vector is perpendicular to the normal vector. So we get an n dot product. So P is on the plane. P prime is on the plane. On the plane. This is the equivalent to n dot product P prime is 0. So this means let P prime be the general XYZ. Now we choose the point P to be 1, 4, 6. Of course, you can use also other points QR. Okay, you get the same equation. Then you get n is 8, -8, -3, 3. So you get so P prime. This will be x minus y minus 6, y minus 4, z minus 6. So you get n dot product p prime is 0. This tells us coordinate form -8 times x component x minus y minus 3 times the y component. This is dot product. And 3 times z minus 6 is 0. Okay, so we get the equation of the plane. Now you can rearrange this to get a neat form. Okay, to get a neat form. Okay. Okay. Now, how do we find the area of the triangle? Find the area of the triangle. Triangle PQR. Okay. Okay. Now remember, if we have two vectors A and B, now the cross product determines the area of the parallelogram. Okay. So area of the parallelogram is A cross B norm. Okay. So we find. So to find the. So here this is PQ, this is PR. Suppose this is. So you can find the area of the parallelogram determined by PQR. Then divide by 2 to get the triangle, area of the triangle. Okay. So PQ cross product PR is the norm of the thing, is the area of the parallelogram. Determined by PQ and PR. Okay. PQ, let's use ST, parallelogram PQ SR. Okay, to find, so we need divide by 2. So we get 1/2 the norm. This will be area of a triangle. Area of triangle PQR. Okay, PQR. So the key is to evaluate the norm of a PQ cross PR. So PQ cross PR, we already find it. Remember, PQ cross PR is, we already find it, -40i minus 15g plus 15k. So it's norm. So PQ cross PR norm will be square root. You can use dot product with itself of this vector, or you use sum of the squares of the component. Then what you finally get is 5 square root 82. Okay, 5 square root 82. So the area of the triangle is half of this norm. Area of a triangle PQR is half of that thing. So it's 5/2 square root 82. Then we are done for this problem. Any questions? Now we do the next topic, volume of a parallel pipette. Volume of a parallel pipette. Okay, a parallel pipette is the following thing. So so it's correspond to, you know, on the 2-dimensional we have parallelogram, and we have rectangle. Okay, then In a three-dimensional space, we have box, we have parallelepiped. Okay, so let's do one example. Let's suppose this. This is A, and this is a B. Okay, so every size, every surface is actually a parallelepiped, is a parallelogram. So this is A. Okay, the base is a parallelogram determined by two vectors A and B. And then the size so every surface is actually a parallelogram. Okay, just plot a parallelogram. Okay, so this one, let's use this parallel. So suppose this is a parallelogram. Let's label the, let's use letters. Let's use letters. So suppose this is a A, B, C, D. Let's use O here. Let's here use A here. Let's use this point to be B, this point to be C, this point to be D, E, F, G. Okay. Okay, this is a parallelogram. So we have determined by three vectors, OB, OA, OC. Now we the parallelogram is of regular shape. Okay, so we can use base times height. Okay, base times height, base times height. So it's a volume of this parallelepiped is volume of this volume of this parallelepiped. So just let me just write volume for short. And then the volume of this parallelepiped is base, area of the base times the height. Area of base times height. Okay, height. Okay, let's now determine the height. So now the base is a parallelogram. How do we determine area of the base? Area of a base. How do we determine area of base of if we know A and B? The vector A and B, remember? The area of the parallelogram is determined by what operation? By what operation? Anyone know? By what operation? Okay. This is given by the cross product. A cross B. Okay, A cross B. Now, A cross B is, the direction is vertical, okay? It's vertical direction. Suppose we put the base to be on a flat horizontal surface, okay? A cross B will be perpendicular to A cross B, okay? So it will be the vertical direction. Then the height, how do we determine the height? Height is, if you find height, you project, so the height is determined by H is norm of C times cosine theta. times cosine theta. Here theta is the angle, the acute angle between C and the vertical direction. Okay. So this will be the projection of C onto the vertical part. Okay, the projection of C on the vertical part. Projection of C on the vertical part. So the volume of V will be, in this case, you see, this you can write as A cross B, this vector, dot product with C. Dot product with C. Okay. Now, if we do this, what we get is, by definition of dot product, A cross B, this vector is norm times norm of C times cosine of theta. Okay. Now, A cross B absolute value or norm, this gives us area of the base. Absolute value C times cosine theta gives us height. Okay. So this is base times base area of the base times height gives us volume. The only ambiguity lies in the fact here we may get a negative value. Okay, in case when theta is cosine theta is negative. So to remove the negative ambiguity, then we take absolute value. Okay, take absolute value. So we get to take absolute value. Okay. Now let's determine what this looks like, A cross B. So the volume is the absolute value of this scalar, A cross B. Now A cross B gives us a vector. Now the vector dot product with a vector gives us a scalar. So this is indeed a scalar. Now suppose we have A is, now we want to determine this, A this operation, A1, A2, A3. B is B1, B2, B3. C is C1, C2, C3. Okay, now we determine, because we know how cross product behaves, okay, how cross product. Now cross product A cross B will be IJK, A1, A2, A3, B1, B2, B3. Okay, so this is A cross B. Okay, A cross B, you see, now C is A cross B. A cross B, so this will be I cross out the column and row that contains I. So we get A1, A1 is no longer there. So cross out, so we get A2, A3, B2, B3. Now remember, 2 by 2 determinant we already done, okay? Minus J, A1, cross out the row and columns that contain J. So we get A1, B1, A3, B3. Plus K. Plus K. So this you get cross out the row and column that contains the K. So this you get A1, A2, B1, B2. Okay, if you let A cross B dot C, then you see if we dot the thing as C, if you dot the thing as C1I plus C2G plus C3K. Remember, I and G, IJK, they are mutually orthogonal, so their dot product are 0. So the only thing that survive is I dot I, so we get 1. J dot J, okay, so we dot J. So here we dot C here, so this we dot C. So the only thing that survive is, so I dot I, J dot J, K dot J, K dot K. So any other terms vanishes because of the orthogonal relation, perpendicular. So what we finally get is, you see, I dot I, then the coefficient is C1. So we get a C1 times A2, A3, B2, B3, okay, minus C2, A1, A2, A3, B1, B3. Now K, coefficients for K dot K, so we get a C3. Now K dot K, we get a 1, okay? So we get a A1, A2, B1, B2. Now this is actually the definition. This is, if you write the thing, so this C1, C2, C3, play the rule of IJK, so this will be C1, C2, C3, A1, A2, A3, B1, B2, B3, okay? Okay, so this is, 3 by 3 determinant by our definition. So now, if we have any 3 by 3 determinant, then we actually get this to be definition. So we just go backwards. So we define a 3 by 3 determinant to be use 2 by 2 determinant. Okay, so this is how we define 3 by 3 determinant. Okay. Now let's do one example. How do we find the volume of a parallel pipette? Okay, let's see one example. Okay, we are given points PQ, RS. P is 2, 0, -1. Q is 4, 1, 0. R is 3, -1, 1. And S is 2, -2, 2. Okay. What we do is we, this parallel pipette, find the volume of the parallel pipette. The volume of the parallel pipette with the 3 adjacent edges. Three adjacent edges, PQ, PR, PS. Okay. Well, we use this notation. So we find the 3 vectors ABC as we did PQ, PR, PS. Use head minus tail. So this you can easily, we have the coordinate, so we can easily find it out. Okay, PQ, let it Q subtract P. Okay, Q, coordinate of Q subtract P. Q is 4, 1, 0. P is 2, 0, -1. So Q subtract P. So we get a 4 subtract 2, so we get a 2. 1 subtract 0, so we get a 1. 0 subtract -1, so we get a 1. Okay, similarly, we work out PR and PS. So PR is R subtract S, so we get a 3 minus 2, 1. -1 minus 0, so we get -1. 1 minus -1, so we get a 2. PS is S subtract P. So 2 subtract 2, 0. -2 subtract 0, -2. 2 subtract -1, 3. Okay. And then we find.
Excuse me, Professor?
Yeah?
Shouldn't PQ be 2, 1, -1?
No, because PQ is Q subtract P. You see, the last entry is 0 subtract -1.
Okay.
Yeah, 0 subtract -1, so we get a positive 1. Yeah?
Yeah.
Okay? Yeah?
Yeah.
Okay. So And then we use the, this notation, A cross B times C. Okay. We choose two vectors, we do cross product, and then for the remaining vector, we do dot product. Dot product. Dot product. So, okay, you may ask, okay, what happens we rearrange the order? Rearrange the order. Now we will see in a moment what happens if we rearrange the order. Okay. So you see PQ, let's choose PQ, PR, PS. So we do PQ cross PR dot PS. Dot PS. Now you see when we do A cross B cross C, sorry, A cross B dot C, sorry, this is A cross B dot C. Okay, so we write C first and then AB. So we write PS first, 0, -2, 3, and then AB. So this is 2, 1, 1. And this is 1, -1, 2. And then this is 3 by 3 determinant. 3 by 3 determinant. So we compute this. Use this following rule. We transform this 3 by 3 determinant by the 2 by 2 determinant. We expand it. Okay, expand. So we get a 2 by 2 determinant. Expand using the first rule. Okay, the first rule is, you see, the first rule of the thing is 0, -2, 3. Okay, so you first expand 0 times, cross out the rule that has this 0 and a rule and a column. Okay, so you see, let me use red to cross out. Okay, so what is remaining is 1, 1, -1, 2. Okay, now for the second entry, -2. So -2 is in the first rule, second column. And then so it should be -2. Okay, -2. So the first -1 and negative sign comes from it's -1, rule number plus column number. Rule number plus column number. So here this -2 is in first rule, second column. Okay, rule number plus column number is 1 plus 2 is 3. So you get a -1 to the power 3. So you get a -1. Okay, and then remaining thing, cross out the rule and columns that has -2. So what is remaining is 2, 1, 1, 2. And then for 3 is, first rule, third column. Rule number plus column number is 1 plus 3 is 4. So -1 to the power 4, you get a 1. Okay, so you get plus 3. This 3 multiply cross. Let's use another color. Sorry, let's use another color. Let's use another color. Let's see. Use pink. Okay, so let's use pink. For -1 to the power 4 is 1. So we get 3 plus 3, and then the remaining thing is cross out the rule and the columns that has 3. So what is remaining is 2y, y, -1. Now you see it's 2 by 2 determinant. Okay, 2 by 2 determinant. 2 by 2 determinant we already defined already. Okay, we defined already. So this you get the first term 0 times anything equal to 0. So -2, so it's 2 times 2 by 2 determinant. Cross multiply 2 times 2 times -1 times 1. And then plus 3. This will be a 2 by 2 determinant is very easy. So you get a 2 times -1 minus 1 times 1. Okay, so what do we get finally? This will be 0, 0, just forget 0. This is 2 times 3, this we get 6. This we get 3 times negative 3, okay? 3 times negative 3, okay? So this will be 6 minus 9. It's negative 3, okay? It's negative 3. Remember, volume should be positive. Volume should be positive. The volume is the absolute value of this quantity, okay? So the volume of the given parallelepiped volume should be absolute value of the negative 3, which is 3, okay? So the volume of the parallelepiped is 3. Now remember, for given parallelepiped, for instance, this parallelepiped, for this parallelepiped, now you can also so here we put AB, vector A, vector B on the ground, on the horizon, this plane determined by OA and OB on the horizontal plane, okay? Now as the base. Now of course, we can also use BC. We can also put the plane determined by vector B, vector C on the ground, on the horizontal ground. And then this will be the volume will be, you see, B cross C, dot product with A, dot product is A. Now remember, volume it should be this. You may possibly get a negative number, so we get an absolute value. Okay, we get an absolute value. So actually, you can switch the order of this cross product. Okay, cross product and the dot product. Rotate corresponding to which face you put it on the horizontal ground. Okay. And you can check. We get the same result, same volume if you use that thing. Okay. Now we already see example how should define 2 by 2 and 3 by 3 determinant. Okay. 2 by 2 and 3 by 3 determinant. We have no choice. We have only one unique choice to determine in the natural way. Okay, determinant of a 2 by 2 and 3 by 3 matrix. Okay, so to summarize, we have defined determinant. 2 by 2 is easy, and then 3 by 3 we expand, and then expand, so we get a bunch of linear combinations of 2 by 2 determinant. Okay, so we transform the 3 by 3 case to the 2 by 2 case, 3 by 3 matrices. Okay, now we consider how to find determinant of n by n matrices. Consider the problem, the question for an n by n matrix, A. So here we assume n is greater or equal than 4, okay, by induction, using induction. Okay, so now we mimic the case. Okay, we mimic the case how we transform the 3 by 3 determinant to the 2 by 2 determinant. Okay, so suppose A is, you write explicitly by its entries, A11. Now it has A1n, so it's n by n. So it's n1, N A N N. Okay, now we give a definition. So this is exactly the same way that we define 3 by 3 matrix, okay, using the definition of a 2 by 2, okay. So we define the minor of the IGS entry. Now with IJ means I column, J I through J column. Okay, so we define the minor. Oh, okay, Mij to be the determinant of the sub matrix that cross out the entry I through J column. Now, if it is 4 dimension 4 by 4, if we cross out a row and a column, okay, that contains the IJ entry, then it will be 3 by 3 matrix. So the minor Mij is the determinant of this matrix, the sub matrix. Sub matrix of A formed by deleting the ith row and jth column. Deleting the ith row and jth column, i.e. the row and columns that contains the ij entry okay. So example, and then cofactor, the ij cofactor, Cij is defined as -1 I plus G Mij. Okay, and then we define determinant of A defined to be G from 1 to N, A the first row expanded by the first row, C1J. Okay, let's see some example. So here Cij is determinant of a smaller matrix. Now we already defined, okay? We already defined 2 and 3, 2 by 2 matrix, 3 by 3 matrix. Now if we have 4 by 4, then its minor will be 3 by 3. So we already know how to determine 3 by 3. Determinant of the 3 by 3 matrix. Okay. Example. Let's do one example. Maybe let's just do one example. By 3 by 3 matrix. So suppose we just choose A to be the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is 3 by 3. Now 3 by 3 we already defined it. Suppose this is just for convenience. Okay, let's just see what is the minor. So what is M11? M11. So the first row, first column. So you find the first row and first column. First row and first column, the entry that has first row and first column. So you see, this is the first row, first column. So you cross out the first row and the first column. Okay, and then the remaining thing will be 5, 8, 6, 9. Okay, so this is determinant, remember? Determinant, 2 by 2 determinant. So this will be 5 times, so this 2 by 2 we already defined, remember? So we get 5 times 9 minus 6 times 8. Okay, so this is the 45 minus 6, 8. So we get this is negative 3. Okay. Now what is C11? What is C11? C11 is a cofactor. The cofactor now 1, 1. I is 1, G is 1. So it's a negative 1 to the power I plus G. I is 1, G is 1 times M11. So it will be negative 1 squared is just 1. So it's M11. So it will be negative 3. Okay. So what is M12? What is M12? M12 is the first row, second column. We use, maybe let's use green. Okay, first row, second column of A. What is, which entry is first row, second column? Which entry? First row, second column. You see, first row, second column. First row, second column. So this will be the entry 2, okay? First row, second column. Okay, then we cross out the row and the column corresponding to 2. Okay, so what is remaining is 4, 7, 6, 9. Okay, so M12 will be, this will be 4, 7, 6, 9. The 2 by 2 determinant we already defined. So this will be 4 times 9 minus 6 times 8. So this will be 36 minus 42. So this will be negative 6. Negative 6. Okay, negative 6. Now what is M13? So what is C12? C12 is negative 1. 1, 2, I is 1, G is 2 times M12. So this will be negative 1 M12. So it will be negative 6, which will be 6. Okay. Then you see what do we get for M13. M13 is we cross out 1, 3. Okay, the first row, third column. First row, third column. So what is first row, third column of A? Let's use pink. Okay, first row, third column. So we cross out the row and the column that has 3. Okay, so what's remaining is so what is remaining? What's remaining is 4, 7, 5, 8. Okay, 4, 7, 5, 8. So it's a 4, 7, 5, 8. So this will be 4 times 8 minus 5 times 7. So this will be 32 minus 35. So it should be negative 3. Okay. So at C13. C13. C13 will be negative 1, 1 plus 3. First row, third column, M13. So it's negative 1 to the power 4. So it's just 1. So it's M13. It's negative 3. Okay, so how do we find determinant of A? By definition, determinant of A will be according to the definition. Okay, A, you know, expand the first entry, expand is the first row. The first row, okay, is the first row. The first row is 1, 2, 3. And then the corresponding minor, the corresponding cofactor, multiply the corresponding cofactor, okay? 1, 2, 3, and the corresponding cofactor. So it's 1, 2, 3. And then multiply the cofactor C12, C12 plus C1, so it's C11, C12, C13. So this will be 1 times C11 is -3, plus 2 times C12 is 6, plus 3 times C13 is -3. So this determinant is -3 plus 12 minus 9. Okay, so this actually you get 0. So you get a 0. Why do you get a 0 here? Let's see if I had any mistake. Okay, C13 is -3. Yeah. Okay. Okay, let me check the answer. Let me check the answer. Use some. So we use elimination to make it upper triangular. So it's 1, 2, 3. Minus that 4 times that thing, 0, -3. 6 minus, so it's -6. Yeah. I think this minus 7, so this you get a 0. 8 minus 14, so you get a -6. 9 minus, so you get a 12 here. Yeah. So this indeed a 0. Okay, so this indeed a 0. So you do this thing, so this you get a 1, 2, 3, 0, -3, -6, 0, 0, 0. Okay, you get a root 0, so this actually determinant has 0. So actually this is singular matrix. If we do invertible operation, you see we get a singular matrix. Singular matrix, the root vectors are linearly dependent, so they lie in one plane. So they have no volume, okay? So the 3 vectors lie on coplanar, so that's no volume. So volume is 0, so the determinant is also 0. Okay. Okay, example. A is ABCD. Remember, we already know the definition. Determinant of A is AD minus BC. So to make this more explicit, let's just using the definition. So what's the minor y1? M11. M11 is we find the first the entry y1 entry. Y1 entry is A. Okay, the y1 entry is A. Okay, y1 entry is A. So we cross out the row and the column that has A. So the remaining thing is D. Okay, so we only have one by one determinant is just the number. So we get a D. Now C11 is -1 to the power root number plus column number 1. 1 plus 1 is 2 times M11. So again D. So M12, what is M12? Use another color, let's use green. So M12 is the first row, second column, the entry is actually first row, second column, you got B, okay? So you cross out the row and column that has B. So what is remaining is C, okay? So C11 is -1, so C12, sorry, C12 is -1 plus 2. So to M12. So you get -1 to the power 3, you get a -1 times C. So you get a negative C, okay? So the determinant of A, by definition, so you get the determinant of A is, according to the first rule, A, B, okay, times C11, C12, add them, okay? C11 is, you see, it's D, so it's A times D, plus B times C12 is C, okay? So it's AD, you see, AD minus BC. Okay, this agree with our old definition, okay? Okay. Some property. Okay. Now let's go back to our definition of determinant. So we have the determinant is defined as this. Defined as A1G, C1G. Okay, J from 1 to N. Now, this C1G is, is also a determinant of N. So if we expand, so here A1G is number, we have nothing to do. If we expand the C1G using N, the definition for N for lower dimension of determinant of an A minus 1 times A minus 1 matrix. So etc. etc. Then we reduce this to N times N minus 2 times N minus 2, etc. etc. So the dimension goes down and down. So finally we reduce to the 2 by 2 matrix, okay? And repeat this above process. Repeat the above process. What we finally get is then we get determinant of A is actually this form. This form. Every term is, look at this, A1 sigma 1, A2 sigma 2, AN sigma N, where sigma is a permutation. Sigma is permutation of N letters, okay? And then here we have sine sigma. We have sine sigma. Okay. So sine sigma, how is sine sigma defined? So sigma, sine sigma is 1 if sigma is even permutation. Even permutation. I.e., you can write it as an even product, a product of even number of transpose permutation. It's -1 if sigma is odd permutation. Odd permutation. So, okay. So even permutation is defined, i.e., in this case, sigma decompose this into even number of a transpose even number of transpose. Now this is actually sigma decomposes into odd number of transpose. Okay, let's see one example. Again, to make this clear, okay? So we just choose the smallest case as possible. So example, we choose n to be 2. N to be 2. Okay, the permutation of symmetric group in n letters, in 2 letters. So the symmetric will be the identity map, change nothing, and then the sigma is 1, 2. Okay, sigma is flip 1 with 2, 1, 2. Okay, so you switch 1, 2. This is switch 2 objects. So this is transpose. So the identity has no transpose. So it's a 0 transpose. So the sign of identity is 1. Sign identity is 1. Sign of sigma 1, 2 is that's 1 transpose. So it's actually odd number. So we get negative 1. So you see, okay, if you have A, so this is 2 by 2, A11, A12, A21, A22. Now you see, according to this definition, determinant A will be, so we have 2 terms corresponding to identity and sigma. So identity will be negative 1 to the sign identity, which is 1 times A1. Identity of 1 is just 1. Okay, identity 1 is 1. Now identity of 2 is just 2, does nothing. So this will be sign identity is 1. So it's A11 times A22. Now subtract. Okay, so we have this is not too early to get determined. So this corresponds to the identity term and the sigma term. So this sigma term, we get sine sigma, which is negative 1. A1 sigma 1. Remember, sigma, what sigma does, it just, you plug in 1, you get a 2. Plug in 2, you get a 1. Okay, A2 sigma 2. Okay, so what do you get is sine sigma is negative 1. Sigma 1 is 2 because it's flip 1, 2. Now sigma 2 is 1, 2, 1. Okay, so this is negative A12, A21. Okay, so the determinant has 2 parts. So determinant A will be the contribution of identity and the contribution of sigma. So this will be A11, A22 minus A12, A21. You see, if you write this as A11, A22, A21, A22. So this will be ABCD. If you write this ABCD, so this actually, you see that this corresponds to exactly AD minus BC. Okay, or so this 1, 2. Okay, 1, 2. So this exactly corresponds to AD times BC. Okay, which is a determinant. Okay, determinant. Oh, this is actually, you see, the determinant. Okay, correspond to AD BC with AD minus BC, which is actually the definition of the 2 by 2 determinant. Okay, 2 by 2 determinant. Okay. Okay, so this, it gives us the general definition. Now, in general, if we expand, how many permutation do we have? How many permutation do we have? We actually have n factorial permutation. So the number of permutation is huge. So in that case, the The formula is really huge, computationally expensive to do that manner. So in general, we don't explain determinant using the definition by the permutation, sum over the permutation. It's too big to do that manner. Okay. Okay, let's see another example. Another example. Let A be this diagonal matrix. Diagonal matrix A11, A22, AN. Okay. If you write as diagonal form, so this will be A11, A22, AN. Then all others terms, and then all other entries are 0. Okay. Now you see determinant of A using definition. So of course here Aij is 0 if G not equal to I. G not equal to I. Now you see the general term determinant of A is by definition, according to definition, sigma a permutation. Okay, it change 1, 2, 3 all the way n to another tuple of this thing. Just rearrange the order. Sigma just rearrange the order. Okay, rearrange the order. Sine sigma A1 sigma 1, A2 sigma 2, AN sigma n. Now remember, if sigma I is not equal to I, so remember AI sigma I is 0. If sigma I differs from I, okay, i.e. this is off diagonal terms, I not equal to G, then Aij will be 0. So the only so if sigma I not equal to I, then the thing will be 0, the product will be 0. So off diagonal terms vanishes. Vanish. So to make sure we have non-zero contribution, so that we need to make sure that sigma I equal to I. So the only non-zero contribution comes from the term that sigma I should equal to I. So the only non-trivial, non-zero contribution comes from the terms that sigma I equal to I. Comes from the term. What does it mean? Sigma I equal to I. What kind of sigma I such that sigma I equal to I? I.e. you plug in I, you get I. You plug in 1, you get 1. Plug in 2, you get 2. Okay, plug in, you get n. So it does no change at all. No change at all. For all I equal to 1, 2, n. I.e. sigma is the identity map. The identity permutation. I.e. it permutes nothing. Permuted nothing. Identity permutation. Okay, so identity permutation, you write it as 0 number of transpose. Sign is 1. So you see in that case, the only contribution is sigma 1 equal to 1, sigma 2 equal to 2. So you get actually determinant of A. By this definition, you get it A11 times A22 times AN. Okay, product of the diagonal terms. Okay, remember what the diagonal matrix does is we plug in E1, then we output E11, E1, okay? E2, we output A22, E2. Now, this means if you plug in the unit box, okay, the unit box corresponds to E1, E2, En. So then its insides are reskewed by 13 factor, okay, by 13 factor. En goes to An, En, okay. So it's every size are reskewed. Every size is reskewed by a certain factor. So the volume of this box is changed, okay? Volume of this box. So remember, determinant is the plus minus volume. Determinant tells us how the volume change. So the volume of this box, N box, is 1, goes to a determinant of this matrix A, absolute value. So here, the right side, so its size is, we take absolute value. So this will be A11, A22, ANN, absolute value, okay? Which is the product of the skew factor, reskew factor, okay? The product of the skew factor, absolute value. So you see, the determinant tells us how the volume changes. The left side is actually volume of the unit box. The right side is the volume of the image. So it's it's possibly no longer just everything is reskewed to a certain factor. Okay. Now we talk about property of determinant. Property of determinant. Right now, the geometric meaning for determinant is actually the change of a volume. So you plug in the unit box and see what do you output, the volume of the output image. So property of determinant. Property of determinant. Property of determinant. For instance, let's show you first property. Determinant of identity is 1. i.e. 1, 1, 0. So you get a 1. Okay. Not just 2 by 2 determinant. Identity matrix has determinant 1. Now if you have a 3 by 3, the determinant is also 1. Okay. It's a trivial because identity does not change anything. So you plug in the unit box, volume 1. Output is unit box, again, volume 1. So the volume does not change. So it's the change is multiplication by 1. Okay, so the identity has determinant 1. Okay, the second property, the determinant changes sign when two roots are exchanged. The determinant changes. Determinant of a matrix changes sign. If you switch, if you exchange two roots, when two roots are exchanged. Here, you may here do the first thing is adjacent rule. Adjacent rules are exchanged. Okay, for non-adjacent rules, you can switch two adjacent rules at a time. Okay, two adjacent rules at a time, and then you can just achieve this by changing adjacent rules. Okay, at a time. So you can exchange any rules. You can exchange any two rules by using adjacent rule exchange. Okay, so Every time you exchange two adjacent rules, then just the determinant change by -1. Okay, so here you see determinant ABCD is we get by definition it is AD minus BC. Now determine if we switch two rules, then what you get is CD AB. And this you get determinant is CD CB minus AD, which is negative. You see, is AD minus BC. Okay, so the sign differ by -1. It differ by -1. Now, so for instance, what happens if we have a 3 by 3 matrix? So that we have 3 rules. So for instance, rule 1, rule 2, rule 3. Now, how do we exchange rule 1 with rule 3? Non-adjacent. Well, you can choose rule 1 with rule 2. So rule 2, rule 1, rule 3. Okay. So every time we exchange, the differ is -1. Okay, differ by -1. Now we do another exchange. R1, R2, R1, R3. We exchange R1 with R3, so we get a R3, R1. Okay, so we get it twice, and then we do it again. So we get a R3, R2, R1. So you see how many times do we get? How many times do we actually use? We use 3 times. Okay, so this we multiply -1, this we multiply -1, so this we multiply -1. So this actually differ by -1 third power. So it's again -1. Okay, -1. So even for 2 rules that are not adjacent, if you switch them, so you can achieve this by adjacent rules, change adjacent rules. So the thing is, the number is always odd number. Okay, the number is always an odd number. So you can check this. If you have 4 by 4 matrix, you choose the first rule with the rule 4. You change rule 1 with rule 4 using this adjacent chain. Okay, changing adjacent rules and see how many times that you need switch to adjacent rules. Okay, and actually that number should definitely be odd number. So we no longer do that thing. We'll skip that. Okay. So every time you switch two adjacent rules, the sign changes by -1. And then, any other general, if you exchange 2 general rules, okay, you can achieve this by odd number of chain adjacent rules. Okay. So again, it's still differ by -1, change by -1. Okay, here for determinant, the rule and the columns, they are actually on the same footing. So you can expand by rule, you can also expand by column. So here, if you switch 2 rules, they differ by -1. If you switch by 2 columns, then it again differ by -1. So example, so if you exchange 2 columns, exchange 2 columns, If you exchange 2 columns, the determinant also differ by -1. So you see, we change determinant of ABCD. We got this is AD minus BC. Now, if we switch the first column with the second column, BD, AC, now what do you get is, according to the definition, BC minus AD. Okay, this is actually negative AD minus BC. So which is negative, the determinant of the first matrix. Okay, so you also get this rule. If you switch 2 columns, then the determinant differ by -1. Okay. The third, if 2 root vectors. To root vectors, or to column vectors. Column vectors are linearly dependent. You know, two vectors are linearly dependent. Linearly dependent means they are parallel. Linearly. So one is a multiple of another, linearly dependent. In that case, it's just parallel. So one vector is a multiple of another vector, parallel. Then determinant is 0. Determinant of A is 0. The reason is if they are parallel, then they does not span the full, for dimension 3. The three vectors does not span the full parallelepiped. So it's just coplanar, okay? Coplanar means there's no volume. Okay, the volume is 0 means the determinant is 0. Or you just see, remember, if they are linearly dependent, then it's singular, not invertible. So the determinant is 0. So let's see this example. 1, 2, 2, 4. So you see the second column, the second row is twice of the first row. Okay, R1 is R1, this is R2. The vector R1, R2 is twice R1. Okay, they are actually a multiple of another, so they are linearly dependent. So they are parallel. So in that case, determinant of the thing will be 0. Determinant of this matrix will be 1, 2, 2, 4. This will be 0. So you see 1 times 4 minus 2 times 2. So you get a 4 minus 4. You got a 0. Okay. So in that case, you also see the column vector. So you see column vector C1. So C1. C2 is 2, 4. Column vector C2 is also twice C1. So column vector is a multiple of another column vector. So in that case, you also get determinant 0. Okay. Now, the determinant is symmetric with respect to row and column. So which means if you flip row with column by the transpose operation, so the determinant does not change. Determinant doesn't change. So let's see this example. So if you have 2 by 2 matrix A, B, C, D, this will be AD minus BC. Okay, if you switch, you see, if you switch this matrix with respect to the diagonal transpose, to the transpose, then you get determinant AD, you got a BC determinant. So this again, you got AD minus CB. Okay, so in this case, BC and CB, they are, multiplication is commutative. Multiplication of scalars are commutative. So this is actually AD minus BC. So this is actually, so determinant of a matrix is the same thing as its determinant of its transpose. Okay. Property 5. Property 5 is this: if we add a multiple of a rule to another rule, then the determinant does not change. So adding a multiple of a rule to another rule does not change determinant, leaves determinant of matrix A unchanged. Okay. Okay, for instance, determinant of 1, 1 is 1. Okay, Now, if we add a multiple, let's just add a y multiple. Add a y multiple over this matrix. So this matrix A. Now we get a multiple matrix. So add a multiple of matrix. Add a multiple of the second row. So B is how do we get B? So we add R1 add twice R. Let's R1 R add R2. Replace R1. So we get a B is add a multiple of rule 2 to rule 1. So it's got a 1, 1, 0, 1. Okay. So determinant of B. Determinant of B, you can check. Determinant of the thing 1, 1, 0, 1. So what you get is 1 times 1 minus 1 times 0 is again 1. So the geometric picture is the following. So A is identity matrix. So you plug in the unit square. So you output the unit square. So this actually you get this identity. So this area is 1. Area is 1. Okay, area is 1. I, G, X, Y. Okay, now B. What B does? If you plug in I, then you get I. If you plug in G, what this matrix B does? You output the second column, which is 1, 1. Okay, second column of B, which is I plus J. I plus J. So what the image of the unit square under the map of B. So if you plug in the unit square, 1x, so it's 1 on y. So it's ig. So what do you get is this is the 1, this is the 1. I goes to I, so here j goes to I plus j. So it will go to this parallelogram. So it will be get this parallelogram. So this parallelogram, you see, it's actually, you see, base is 1, height is 1. So it's 1 times 1. So again, area equal to 1. Area does not change. Okay, it just changes the direction, but it does not change the height. Okay, it does not change the height. Okay, does not change the height. Okay. Property 6. If a rule is multiplied by lambda, if a rule is multiplied by lambda, then the height is actually multiplied by lambda. Then the determinant, should be multiplied by lambda again. Then determinant is also multiplied by lambda. So you skew one dimensional thing by lambda, just multiply the height by lambda. Okay, so for instance, if you skew this thing, determinant lambda A, lambda B, CD. So you get a lambda A times D minus lambda B times C. So you get a lambda AD minus BC. Okay, so here A is ABCD. So this is actually lambda determinant A. Okay. Now, if we definition of multiplication of a matrix by a scalar is we multiply every entry by lambda. So i.e., or we multiply every rule by lambda. That is, we get multiply every rule by lambda. I.e., we skew every dimension by lambda. Height, base, lengthwise height by lambda, rescue by lambda. So the volume will change by lambda cube. Okay, the volume will change by lambda cube. If it's three-dimensional. If it's two-dimensional, it will change by lambda square. So for the 2x2 determinant, then you see this will be lambda A times lambda D minus lambda B times lambda C. So this will be factor lambda squared, so lambda squared AD minus BC. So this will be lambda squared dA, determinant of A. So where does the square come from? The square comes from the fact that A is 2x2 matrix. Okay, it's 2x2 matrix. If it is 3x3 matrix, then you sort of multiply the determinant of A by lambda cube. Okay, so if A is lambda, if A is n by n matrix, if n is n by n matrix, then we have determinant of lambda A. Be careful here. Then we get lambda to the power n determinant of A. Think about the volume. Think about the volume. If we rescue every factor by lambda, the volume should have, skewed by lambda to the power n. Okay. Now the next property, property 7, determinant A times B equals determinant A times determinant B. Okay. Now, of course, determinant is a number. So for number, you can always, two numbers multiplication is commutative. So you switch them. Okay, so you got determinant BA. Okay, you see, two matrices AB, their product AB not necessarily equal to BA. However, this, if you do determinant, they will recover the commutative property. Okay, so matrix is not commutative. However, if you do determinant, you recover the commutative property again. Okay, so we recover the commutative property again if we apply determinant to matrix product. Okay, so this is a nice property. This is a nice property. Okay, so it's really tedious to prove that determinant A times B is determinant A times determinant B, but the idea is easier. The idea is very easy to explain. You think about this as operation. Okay, A daughter B, A times B means you put a vector, you do operation B, you get a B, BV, then plug in this to the machine A, you get ABV, ABV. Okay, so this is ABV. So this is the same thing as you do the composition AB. Okay, ABV. This is the, remember the matrix multiplication is actually comes from this composition. Okay, we define matrix multiplication such that they think it are equivalent. They think are equivalent. So if you think about this idea, so the matrix B, so change about area. So what A does is you change area of the unit thing into determinant of A. Okay. Now B is you change. So this is A. B, you get a determinant of B. Okay. So the composition should multiply. Okay. The composition should multiply. Okay. Should multiply. So this is in terms of area. Okay. In terms of area. The only ambiguity here is the sign. Okay. The only ambiguity is the sign. You need to change. You need to take care about the sign plus minus y. Okay. Because volume and area is just positive. So the only thing is the direction is the sign. The determinant is negative if it flip the sign, flip direction. So if you're thinking about it, if one change sign, the other does not change sign, the composition does not change sign. Okay. If one both change sign, A change sign, B change sign, then the product change twice. Then it does not. So the total does not change sign. So the sign ambiguity can be easily checked. Okay. So think about this in terms of the skew factor of what a matrix does is actually change the volume in by the determinant. If you think about this, this will be trivial. Okay, think about this, this will be trivial. So for instance, if you let do one example, plot one picture. So suppose it's the box that you plug into A, for instance, plug into B also doesn't matter. So let's first do B, for instance. Then you may get another, you may get a parallelogram. Okay, you may get a parallelogram. Then this area is area 1. Now this area is, remember, determinant tells us how area changes. Area change is determinant of B, absolute value. Now at this thing, you can choose a small box, okay, small box, you change it here, small box, and then you apply A, you may get, here, okay. Now this thing, multiplication by the area is multiplication by determinant A, okay. When the area is 1, we output determinant of A, of the value. Now the corresponding change is multiplication by determinant A. So the total thing is AB, okay? Total thing change is AB. So if you have any box, you just find by, the change is by multiplication of determinant A. So what do you finally get? Determinant of AB, also value. So equal to determinant of A times determinant of B, also value. Now the sign ambiguity can change by thinking about the direction. So finally we have A, determinant AB is determinant A times determinant B. Okay. Now of course this will be a disaster if you try to use algebra. The algebra should work. The algebra should work, okay, definitely work. But if you try to arrange the algebra such that you get the thing, that will be a disaster to read. Okay, so we will try to avoid that manner. Okay, so another property is determinant A, and its determinant A inverse is also property 8, determinant of A times determinant of A inverse. By the property of determinant, last step, this determinant A times A inverse. So we get a determinant of I, which is the identity, is 1. Okay, so we get a determinant of A inverse is inverse of determinant. Okay, so it's a nice property. So property 9, let me write down this property. So if A is diagonal, A y, A n, then determinant of A, we already proved this, is a product of the diagonal entries. Okay, now if A is upper triangular, if A is triangular or not just upper triangular, then determinant of A equals the product of the diagonal entries. Next time we will give example. Okay, now it's very easy to check using the definition from this follows from 5 and 9. Okay, this follows from property 5 and property 9. because for triangular matrix, you can add the row and columns such that you get diagonal matrices. So this follows from property 5, follows from 5 and 9. Okay, think about this. Next time we will talk about examples, and we will compute determinant. Okay. Okay. Let me stop here and continue on next week.